Question 1. A plant grows 2 centimeters per day, starting at 10 centimeters. Write a linear model for the height after d days, then find the height after 7 days. Let's begin by identifying what kind of model this situation describes. The plant grows by a constant amount each day, so a linear model is appropriate. A linear model has the form h equals m times d plus b. The slope m represents how much the height changes per day, and the intercept b represents the starting height. The problem states that the plant grows 2 centimeters per day. That tells us the rate of change is 2 centimeters for each additional day, so the slope is m equals 2. We're also told that the starting height is 10 centimeters. This occurs at day 0, before any growth has taken place, so the intercept is b equals 10. Combining these values gives the model h equals 2d plus 10. Now we use the model to make a prediction. After 7 days, substitute d equals 7 into the equation. 2 times 7 plus 10 equals 24. So the plant's height after 7 days is 24 centimeters. On the SAT, it's important to interpret the equation in context. This model means the plant starts at 10 centimeters and increases by 2 centimeters every day. A final check. When d equals 0, the model returns a height of 10, which matches the situation. When the model agrees with the context, your reasoning is sound. Question 2. A bike rental shop charges different amounts depending on the number of days. When the rental period is 1 day, the cost is $18. For 2 days, the cost is $26. For 3 days, it is $34, and for 4 days, it is $42. Look carefully at how the cost changes as the number of days increases. Estimate the cost for 2.5 days. Then decide whether this estimate is an interpolation or an extrapolation. Let's walk through this step by step. We're given a table showing the cost of renting a bike over several days. On day 1, the cost is $18. On day 2, it's $26. On day 3, it's $34. And on day 4, it's $42. First, notice the pattern. Each day, the cost increases by the same amount. From 18 to 26 is an increase of $8. From 26 to 34 is also $8. And from 34 to 42, again, $8. That tells us this relationship is linear, with a slope of $8 per day. So we start by writing a linear model in the form cost equals 8 times d plus b. To find the starting value, b, we use one of the data points. When d equals 1, the cost is 18. So we substitute 18 equals 8 times 1 plus b. That gives us b equals 10. Our model is now cost equals 8d plus 10. Next, we estimate the cost for 2.5 days. We plug 2.5 into the model. 8 times 2.5 is 20, and 20 plus 10 equals 30. So the estimated cost is $30. Finally, we decide whether this is interpolation or extrapolation. Since 2.5 is between 1 and 4, and those values are inside the given data range, this is interpolation. Key idea. When your x value is inside the data range, a linear estimate like this is reasonable and reliable. Question 3. 2 bike rental shops charge different prices. Shop A charges a $12 start fee, then $3 per hour. Shop B charges an $18 start fee, then $2 per hour. Here are your tasks. First, write an equation for each shop. Cost A, h, and cost B, h. Next, find the break-even point algebraically, show your work. Then, after the break-even point, when is shop B $10 cheaper than shop A? Finally, explain why shop B eventually becomes cheaper even though it starts higher. Alright, let's go through question 3 together. We'll start by turning each sentence into a linear model, and then use those models to answer each part of the question step by step. The key to this problem is to read each sentence as a linear model. Start fee is the intercept, and cost per hour is the slope. For shop A, the cost starts at $12 and increases by $3 each hour, so cost A, H, equals 12 plus 3H. For shop B, the cost starts at $18 and increases by $2 each hour, so cost B, H, equals 18 plus 2H. Now for the break-even point. Break-even means the costs are equal, so we set the two expressions equal. 12 plus 3H equals 18 plus 2H. Subtract 2H from both sides to compare the hourly rates, giving 12 plus H equals 18. Then subtract 12, so H equals 6. Plug back in. Cost A, 6, equals 12 plus 3 6 equals 30, and cost B, 6, equals 18 plus 2 6 equals 30, so the break-even point is 6 hours, $30. On the graph, that's exactly where the two lines intersect. Next, when is shop B $10 cheaper after break-even? We want A minus B equals 10. 12 plus 3, H, minus 18, plus 2, H, equals 10. 12 plus 3H, minus 18 plus 2H, equals 10. Simplify. 12 plus 3H minus 18 minus 2H equals 10, so H minus 6 equals 10, which gives H equals 16. At 16 hours, A costs 12 plus 48 equals 60, and B costs 18 plus 32 equals 50, so B is $10 cheaper. Finally, why does B become cheaper even though it starts higher? Shop B begins $6 higher, but its hourly rate is $1 less per hour. After the intersection at 6 hours, that $1 per hour advantage keeps increasing, so B stays cheaper and the gap grows by $1 each hour. SAT tip. In linear models, the intersection answers when are they equal, and the difference in slopes tells you how fast the gap changes. Now, let's move on to question 4. A phone battery starts at 80%. While streaming, the battery level decreases by 2 percentage points per hour. You are asked to do two things. First, write a linear model that represents the battery level after H hours. Second, use that model to find the battery level after 6 hours. You may refer to the graph, which shows the starting battery level and the rate at which it decreases over time. Now, let's go through the solution to question 4. This situation is modeled using a linear function because the battery changes at a constant rate over time. We are told that the battery starts at 80%. This value represents the initial amount, which is the y-intercept of the model. Next, the battery decreases by 2 percentage points per hour. Since the battery is going down, the rate of change is negative. This gives us a slope of -2. Putting these pieces together, we can write the linear model as B of H equals 80 minus 2H. In this equation, H represents the number of hours of streaming, and B of H represents the remaining battery percentage. To find the battery level after 6 hours, we substitute H equals 6 into the model. Doing this calculation gives 80 minus 12, which equals 68. This means that after 6 hours of streaming, the phone's battery level is 68%. The graph confirms this result. At H equals 6, the point on the line lines up with a battery level slightly below 70%, consistent with our calculation. This problem highlights an important idea. In linear models, the intercept represents the starting value, and the slope tells us how fast the quantity changes over time. Question 5. A distance time graph is shown. The line represents a linear model for an object's motion. Notice that the graph starts at -30 miles when time is 0. Your task is to think carefully about what this means. Does a negative distance represent a real situation? And more importantly, for what time values does this model actually make sense? You are not asked to compute anything here. Instead, focus on interpretation. Take a moment to think about what the model says, and what it does not say. Now let's begin the explanation for question 5. The equation shown by the graph is distance equals 60t minus 30. The slope of 60 means the object is moving at a constant speed of 60 miles per hour. That part of the model is clear and reasonable. The intercept, however, is negative 30. This means that at time 0, the model predicts a distance of minus 30 miles. In the real world, distance is rarely negative. So this value should immediately make you pause. This does not mean the equation is wrong. It means the equation is being used outside its meaningful context. Mathematical models often describe trends, not entire histories. In this case, the model likely describes motion after a certain starting time, not from time 0 itself. That is why we focus on the meaningful time range, specifically values of t greater than or equal to 0 where the situation actually makes sense. This question is testing whether you understand that a model can be mathematically correct while still being unrealistic for some inputs. Always ask yourself not just, does the math work? But also, does this answer represent a real situation? That habit is essential for strong data reasoning. Now let's look at question 6. This graph shows the number of users for an app from day 1 to day 5. A linear model has been drawn based on this data. First, use the graph to estimate the number of users on day 10. Next, decide whether this estimate is interpolation or extrapolation. Finally, think about whether this estimate is reliable, and be ready to explain why or why not. Take about 30 seconds to think before we walk through the explanation. Now, let's begin the explanation for question 6. From the graph, the linear trend suggests that the number of users on day 10 is about 90. This value comes from extending the straight line beyond the observed data points. However, this estimate is an example of extrapolation, not interpolation. The data used to create the model only covers days 1 through 5, while day 10 lies clearly outside that range. When we extrapolate, we assume that the same growth rate continues unchanged. Mathematically, the model still works, and the calculation is valid. But in real-world situations, this assumption is often risky. User growth may slow down, level off, or even decrease due to factors such as market saturation, competition, or changes in user behavior. None of these factors are captured in the original data. That is why extrapolated predictions are less reliable than interpolated ones. Interpolation stays within known information, while extrapolation extends beyond what the data can truly support. The key takeaway is this: a model can be mathematically correct and still lead to a poor prediction if it is applied outside its meaningful range. On the SAT, recognizing this limitation is often more important than performing the calculation itself. Now, let's move on to question 7. You are given the same set of data points and two different linear models, Model A and Model B. Both lines seem reasonable at first glance, but only one is the better choice. Your task is to decide which model more appropriately represents the data. As you think about this, focus on how closely each line fits the points and whether either model misrepresents the trend. Take about 30 seconds to think before we go through the explanation. Now, let's begin the explanation for question 7. When choosing between two linear models, the key question is not which line looks nicer, but which one represents the data more accurately. In this graph, both Model A and Model B are straight lines, and both pass near the data points. However, accuracy matters within the range where data actually exists. Looking closely, Model A rises more steeply and begins to overestimate the values toward the right side of the observed data. While this line might work outside the data range, that is not our main concern here. Model B, on the other hand, stays closer to the data points across the entire observed range. It reflects the actual trends shown by the data without exaggerating future values. This highlights an important idea. A good model fits the data you have, not the data you imagine. Extrapolating beyond the data can be risky, especially when there is no evidence to support it. In linear modeling, small differences in slope can lead to large differences in predictions. That is why we prioritize the model that minimizes error where the data exists. So even though both models are mathematically valid, Model B is the better choice because it more faithfully represents the real-world data. Always remember, the best model is not the most aggressive one, but the most accurate one within context. Question 8. A population starts at 500 and increases by 6% each year. Take a moment to read the statement carefully. This is not a linear situation. The population does not increase by a fixed amount. Instead, it grows by a fixed percentage each year. Your task is to find the population after 3 years. Before calculating anything, think about these questions. What is the starting value? What does 6% each year mean in terms of a multiplier? How many steps does 3 years correspond to? You do not need to rush. Focus on identifying the structure of the model first. When you are ready, move on to the explanation. Now, let's go through the solution step by step. We are told that the population starts at 500. That means when the step number n is 0, the value is 500. Next, the problem says the population increases by 6% each year. An increase of 6% does not mean add 6. It means we multiply by 1.06 each step. So the multiplier in this situation is 1.06. Putting these pieces together, we can write an exponential model. Value equals 500 times 1.06 to the power of n. Now we identify how many steps we need. The question asks for the population after 3 years, so n equals 3. N equals 3. Substituting into the model gives 500 times 1.06 cubed. Evaluating this expression gives a value of approximately 596. So after 3 years, the population is about 596 people. The key idea to remember is this. In exponential models, always identify the starting value, the multiplier, and the number of steps before calculating. Structure first, calculation second. Now, let's look at question 9. A device costs $200, and it loses 15% of its value each month. Your task is simple. What will the value of the device be after 2 months? Think carefully about how this value is changing over time. Is the value decreasing by a fixed amount, or by a fixed percentage? Take about 30 seconds to think before moving on to the explanation. Now, let's begin the explanation for question 9. In this problem, the key idea is that the value is changing by a percentage, not by a fixed amount. Each month, the device loses 15% of its current value. Whenever a quantity changes by the same percentage each step, we use an exponential model. The device starts at $200. This is our initial value, and it corresponds to step 0. A 15% loss means we keep 85% of the value each month. So the multiplier is 0.85. Using this information, we can write the model as value equals 200 times 0.85 to the power of n. Here, n represents the number of months. Since we are asked for the value after 2 months, we set n equal to 2. Now we calculate. 200 times 0.85 squared gives a value of $144.5. Notice an important pattern. Because this is decay, the multiplier is between 0 and 1. That tells us the value gets smaller each step, but it never drops instantly. The key takeaway is this. When you see repeated percent decrease, think exponential first, then identify the multiplier, and only then calculate. Question 10. A savings balance starts at $50 and decreases by 20% each week. The question is, what is the balance after 4 weeks? Before calculating, pause and think. What is the starting value? What happens each week, and how many times does that change occur? Question 10. Solution. This is exponential decay, because the balance changes by a constant percent each week, not by a constant amount. Start with the initial value, $50. A decrease of 20% each week means you keep 80% each week. So the weekly multiplier is 0.8. Now focus on the phrase, after 4 weeks. That means the multiplier is applied 4 times. So the model is, balance equals 50 times 0.8 to the 4th power. Compute step by step to avoid mistakes. 0.8 squared is 0.64. Then square again for the 4th power. 0.64 times 0.64 equals 0.4096. Now multiply by 50. 50 times 0.4096 equals 20.48. So the balance after 4 weeks is about $20.5. SAT tip. When you see percent change each period, always convert it to a multiplier first. Decrease 20%, becomes, multiply by 0.8. Then make sure the exponent matches the number of periods. Here, 4 weeks means power 4. Question 11. A table shows an exponential pattern. When n equals 0, n equals 0, the value is 100. When n equals 2, n equals 2, the value is 121. The question is, what is the multiplier per step? Before calculating, pause and think. The value didn't change in 1 step, it changed over 2 steps. So ask yourself, what number, multiplied twice, turns 100 into 121? Question 11. Explanation. Let's slow this down. We are told that the value changes from 100 to 121. But notice something important. This change does not happen in 1 step. It happens over 2 steps. That means we cannot ask, what number multiplies 100 once? Instead, we have to ask, what number, multiplied twice, gives 121? So we write the model, 100 times the multiplier squared equals 121. Divide both sides by 100. Now we have, the multiplier squared is 1.21. At this point, many students stop. But this number, 1.21, is not the multiplier. It represents 2 steps, not 1. So we take the square root. The multiplier is 1.1. Key idea. When steps are skipped, you don't guess, you use powers. Question 12. Here is an exponential model. The value is given by 300 times, 0.92, to the power of n. Take a moment to read the expression. The question is, what percent change happens at each step? Before calculating anything, pause and think. Where is the rate hidden? In the exponent, or in the multiplier? And what does a number slightly less than 1 usually mean in an exponential model? Question 12. Explanation. Let's break this down carefully. The model is, value equals 300 times 0.92 to the power n. In an exponential model, the number being multiplied each step is the base, here, 0.92. That base is the multiplier per step. Now translate that multiplier into a percent change. Think of 1.00 as no change. If the multiplier were 1.06, we'd say a 6% increase, because 1.06 equals 1 plus 0.06. Here it's 0.92, which is less than 1, so it must be decay. Write it as a change from 1. 0.92 equals 1 minus 0.08. That tells you the value keeps 92% each step and loses 8% each step. So the percent change is an 8% decrease per step. Notice the language. It's not minus 8 points each step. It's minus 8% of the current value, so the amount lost gets smaller over time. A quick check. After one step, the value would be 300 times 0.92 equals 276. That's 24 less than 300, and 24 is 8% of 300, consistent. Key idea. In exponential models, percent decrease equals 1 minus the multiplier, and percent increase equals multiplier minus 1. Read the base first, then state the rate, and n just counts the steps. Question 13. We are given an exponential model. Value equals 300 times 0.92 to the power of n. The question is, what percent change happens each step? Before doing any calculations, pause and read the model carefully. This time, we are not asked to find a value. We are asked to interpret the multiplier. Focus on the number multiplying n. 0.92. Ask yourself, is this number greater than 1, or less than 1? And what does that tell us about growth or decay? Question 13. Let's break it down carefully. The given model is value equals 300 times 0.92 to the power of n. In any exponential model, the key to understanding the rate of change is the multiplier. Here, the multiplier is 0.92. Now compare it to 1. Because 0.92 is less than 1, this model represents decay, not growth. To find the percent change, we ask a simple question: how far is the multiplier from 1? We calculate 1 minus 0.92. That equals 0.08. This tells us that the value decreases by 8% each step. It's important to notice what this means conceptually. Each step, the value is multiplied by 92% of its previous value. That remaining 8% is lost. This interpretation works for any exponential model. If the multiplier is greater than 1, the percent change is growth. If the multiplier is less than 1, the percent change is decay. And the amount of change is always 1 minus the multiplier. Key idea: you don't need to compute values to understand the rate. The multiplier tells you the percent change immediately. That completes question 13. Question 14. Which part of the graph shows a faster rate of change? Take a moment to look carefully at the graph. Two different intervals are shown, one on the left and one on the right. As you think about your answer, focus on the interval itself, not how high the graph is. Ask yourself this: which part of the graph increases more per step along the x-axis? Pause here and decide which interval is changing faster. All right, let's go over question 14. The right interval shows a faster rate of change. The left interval starts at a higher value on the graph. However, its increase from point to point is smaller. In contrast, the right interval starts lower, but it increases more for each step along the x-axis. Rate of change depends on slope, not on height. Even if one part of the graph is higher, it is not changing faster unless its slope is steeper. In this graph, the slope of the right interval is steeper, so the right interval has the faster rate of change. Question 15. Two pieces of a graph are shown. Over which interval does the value increase at a faster rate? Take a moment to look at both intervals. The graph shows labeled points, so you can compare how much the value changes over the same x interval. As before, do not focus on which part of the graph is higher. Instead, compare how quickly the values increase as x increases. Pause here and decide which interval has the faster rate of change. Alright, let's go over question 15. Interval B increases at a faster rate. To compare rates of change, we look at how much the value increases over the same change in x. In interval A, the graph goes from the point 0, 6 to the point 4, 8. Over this interval, x increases by 4 and y increases by 2. This means the rate of change in interval A is 2 units of y for every 4 units of x. Now look at interval B. The graph goes from the point 4, 5 to the point 8, 11. Here again, x increases by 4, but y increases by 6. Because interval B shows a larger increase in y over the same change in x, its slope is steeper. A steeper slope means a faster rate of change. This problem highlights an important idea for the SAT. You cannot judge rate of change by height alone. Even though interval A starts at a higher value, it does not increase as quickly. When x intervals are the same, the interval with the greater rise has the faster rate of change. In this case, that interval is interval B. Question 16. A piecewise graph shows two different rules over different intervals. Which interval represents the faster rate of change, and why? Choose the best explanation. Look carefully at both intervals. As before, do not focus on starting height. Compare how much the value increases over similar x intervals. Pause here and decide which interval is increasing faster and which explanation best supports that conclusion. Alright, let's go over question 16. Interval B increases at a faster rate. In a piecewise graph, each interval can follow a different rule. To compare rates of change, we look at how much the value increases relative to the change in x within each interval. In interval A, the graph rises slowly from left to right. Although it starts at a higher value, the increase over its interval is small. In interval B, the graph starts lower, but it rises much more over a similar horizontal distance. This means that for each unit increase in x, the value increases by a larger amount in interval B because interval B has a steeper slope. It represents a faster rate of change. This is why comparing starting height alone leads to incorrect conclusions. A graph that begins higher is not necessarily changing faster. When the question asks for both the faster interval and the best explanation, the correct reasoning must be based on slope. Here, interval B rises more over a similar x interval, so interval B increases at the faster rate. Question 17. The graph shows an exponential model for the value of a quantity over time. Which statement must be true? 4 choices are given. Look at how the value changes as time increases. Do not focus on the exact numbers. Instead, think about what kind of change an exponential model represents. Pause here and decide which statement must always be true for this model. Alright, let's go over question 17. The correct answer is choice B. In an exponential model, the quantity increases by the same percentage during each time period. This does not mean the quantity increases by the same amount each time. As the value gets larger, the amount of increase also becomes larger, even though the percentage change stays constant. This is why choice A is incorrect. A constant amount of change describes a linear model, not an exponential one. Choice C is also incorrect. An exponential model does not necessarily double after a fixed number of time periods unless that information is given. Choice D is incorrect as well. The graph shows the change becoming steeper over time, not faster at the beginning. The key idea is this: exponential growth is defined by a constant percentage change. Therefore, the statement that must be true is choice B. Now, let's move on to question 18. A quantity is measured over time and modeled using the graph shown. Which model best describes the relationship? Let's look at question 18. The correct answer is C. This graph represents an exponential model because the value increases by a constant percentage, not by a constant amount. In a linear model, equal time intervals produce equal increases. That is not happening here. Instead, the increase becomes larger as the value grows, which is the key feature of exponential growth. Choice B is incorrect because a curve can look smooth without being linear. Choice D is also incorrect because exponential growth does not increase faster at the beginning. What matters is how the value changes, not just the shape of the graph. Now, let's move on to question 19. An exponential model describes the value of a quantity over time. The value increases by 15% each time period. Which statement must be true? Let's look at question 19. The correct answer is C. In an exponential model, the value increases by a constant percentage each time period. That means the change depends on the current value, not on adding the same amount each time. Choice A describes a linear model. Choice B is incorrect because exponential growth does not increase faster at the beginning. Choice D is also incorrect, since exponential models do not naturally stop increasing. The key idea is that exponential change is based on a constant ratio or percentage. Now, let's move on to question 20. The graph shows a model fit to data for a quantity over time. The solid curve represents the model within the observed data range. The dashed curve shows the model extended beyond that range. Which statement is best supported? Let's look at question 20. The correct answer is C. The solid curve is supported by observed data, so predictions in that region are more reliable. The dashed curve extends the model beyond the observed data range. This extension is called extrapolation. Because extrapolation relies on assumptions beyond the data, predictions in that region are less certain. The key idea is that models are strongest where data exists and weaker when extended beyond it.